Consider the bar-tailed godwit. This shorebird launches from Alaska and flies 12,000 kilometers across the Pacific Ocean without landing a single time. To survive a non-stop flight lasting more than a week, they physically alter their bodies before takeoff. They shrink their internal organs to save weight, effectively turning themselves into living, winged fuel tanks. Out there over the open ocean, the margin for error is brutal. Drifting off course early in the journey becomes a fatal miss. There is nowhere to rest and no safety net. For these migrants, precise navigation determines whether they reach their destination or vanish somewhere over the Pacific. The Earth is wrapped in a magnetic field generated by molten iron churning deep in its core. But this field is incredibly weak, measuring roughly 50 microtesla. To put that in perspective, the Earth's magnetic field is up to 100 times weaker than the cheap fridge magnet, holding up your grocery list. It is barely a whisper. For decades, scientists guessed that birds read this faint signal using tiny deposits of iron in their beaks, essentially carrying around a physical, built-in compass needle. If that purely mechanical theory held up, the mystery would be solved. But tests on living birds started yielding results that pointed toward a system far stranger than a piece of iron. When researchers placed migratory birds in total darkness, their magnetic sense completely vanished. But the moment the room was illuminated with blue or green light, the birds reoriented themselves. Their internal compass flickered back to life. A standard iron needle works perfectly well in the dark. This absolute reliance on light suggests the sensor is actually a light-sensitive protein, specifically one called cryptochrome, located inside the retina. The navigation hardware appears to be entirely optical. This little bird may be literally seeing the Earth's magnetic field layered over its normal vision. European robins lose their magnetic bearings when exposed to extremely weak radio noise, waves flipping back and forth millions of times every second. A solid chunk of iron is completely unaffected by minute radio frequencies, but these specific frequencies act as a severe disruptor at microscopic scales. Only incredibly delicate subatomic systems possess the exact vulnerability to be thrown off balance by faint oscillating waves. Because these radio waves are far too weak to push a physical needle, but possess the exact frequency needed to scramble electron spins, they point towards a navigation system governed by the rules of quantum mechanics. Here is how that quantum compass actually runs. A particle of blue light enters the bird's eye and strikes the cryptochrome protein, kicking a single electron loose. That loose electron jumps along a microscopic chain of amino acids, acting like a spark running down a tiny molecular wire. When it moves, it leaves a partner, creating a radical pair of linked electrons. They are so sensitive that the faint magnetic field physically tilts their orientation. Depending on that tilt, the protein churns out specific chemical products inside the eye. The bird's brain then reads those resulting chemical concentrations, translating a subatomic reaction into a shifting visual overlay that steers the animal across continents. If you extract cryptochrome from a migrating robin and test it in a lab, you find a highly sensitive, optimized sensor tuned by evolution. Compare that to a species that stays put, like a backyard chicken. They possess the same protein, but it is a basic version. Nature optimized the hardware only in the birds that needed it. But this specialized sensor has a quirk. It doesn't read strict north or south. It measures the downward tilt of the magnetic field lines against the pole of gravity, telling the bird to head either poleward or equatorward. Because of this, the compass fails at the magnetic equator. There, the field lines lie flat at 0 degrees, providing no downward tilt to measure, leaving the birds to fly in random directions. These geographical blind spots and evolutionary upgrades match the expected behavior of the quantum compass model precisely. Picture that tiny robin lifting off a branch in Sweden, heading into the freezing dark, driven by internal geometry. It finds its way using a global field, light striking its retina, a pair of spinning electrons, and a map painted directly onto its vision. Human scientists require heavily shielded laboratories and super-cooled equipment just to briefly stabilize these exact quantum behaviors. The robin simply carries them in its head on the way to Africa. Millions of years before we wrote down the laws of physics, nature was already using them to solve the problem of getting lost. If exploring the hidden systems that keep our planet running is your kind of thing, you are in the right place. Hit that subscribe button and give this video a like to help more curious minds find us. Drop a comment below and tell me what mystery you want us to decode next. Thanks for watching, and I'll see you in the next one.